Good morning, everybody. I hope you had a nice weekend. Today we are going to be working with the correlations and how it sort of works. Let me get this on screen. How this sort of works is I put all the classroom stuff sort of in that last set of notes. For correlations, I, I think you've run across them before, not the calculation component of them, but sort of an understanding of correlations. You would have at least run across it in some detail in intro. I think that stuff is pretty straightforward. There's a couple things that I'll include as we go through today that I thought might be unclear, but I didn't think I needed to make a video for the first correlation lecture. So how this will tend to work as we go forward, and now we actually have real formulas for us to deal with, and today we're going to have 3 of them. I am spending one day where I'm putting all of the conceptual stuff up. So sometimes that's going to be long, like in the case with correlations. Sometimes that'll actually be a little bit shorter, and that's going to be the case with our next topic, regression. But the next day, we will have either a set of notes. I don't think so. I think for when we're working through the formulas, it's just going to be video. If you have data sets printed out and ready to go, you follow along. And the work on that worksheet that has the data set that we're using in class and then with lab, that will sort of be the notes for how to do the analysis. So I'm going to try to keep the 2 parts separate. Here's everything you need to know in this case about correlations in one set of notes, and then us walking through step by step the formulas sort of in a separate place. So depending on what your need is, you can go back and forth between them. If after today there are still, of course, questions from that set of notes and correlations that I didn't cover, just let me know, send me an email, and I'll be glad to address it. But I think I'll pick up a little bit of the things that I thought were worthwhile. That might require a couple statements about it, but I don't think it's really that much. So let's just sort of go plow forward on these correlations and these problems. Excuse me, I'm very parched today, by the way, just letting you know. All right, that's extraordinarily professional, and I apologize. Okay, so here we're going to have 3 different sets of correlations. So there are 3 kinds of correlations that you're going to be responsible for. The Pearson R, which is truthfully in practice about 95% of the correlations that are done, and we just call it the Pearson. If it's never specified, it's a Pearson. That's how commonplace it is. The Spearman row, point by serial, are for special sets of data, but they are sets of data that we will run across in psychology. So it's important to have these things in here. Now, notice that there's a few things that we need, and there are a few brand new things as we're heading forward. I sort of said that it's going to feel slightly different after we get past standard deviation, which was all remedial stuff. Now we're going to get into stuff that is, it's going to feel more like statistics. So here we go. You're going to be using both with the video here and the lab video, and certainly anytime we're going through a formula, you're going to be asked to work along with me. So have that pause button ready and have the stuff ready to work. We'll go ahead and have you work it out and then start the video from that point again. And then when we get to the next step, pause, you work it out. When you're finished, then unpause it and go forward. So that's really how these things are going to work. Things you do need though. On Canvas, loaded, I don't know, a week and a half ago, are the classroom data sets. And I put it all in one big file, so just print everything up. You're going to need all of them. Those are the data sets which are being used in this, which is sort of the classroom walkthrough, the first time we go through, and the data sets for the lab. So there'll be another one of these just working through a different set of problems on lab day. So make sure that you have those printed out. They don't take up the full page, and you do the work on that particular page. And that would be like us working through it in class. So that is going to be your walkthrough that you have to study from and follow. Although there are others all over the place, oddly enough. So you need those data sets printed. If you haven't done that, print them out, at least the ones that we need. So today it's going to be the Pearson, the Spearman, and the point by serial. And then for the lab this week, of course, there's a Pearson data set, a Spearman data set, and a point by serial data set. So if you only print out individual pages, make sure you have all of those. But you're going to need the 3, 4 from the classroom for today. So make sure those are printed out. And obviously now we're going to need a calculator. So make sure you have that, and obviously something to write with. I shouldn't need to say that, but we all scramble for a pencil once in a while. So those are things that you're going to need. Things that are changing. So certainly the formulas are gonna look like formulas. We're past the standard deviation as our high point, and you're gonna see we're gonna zip right by that very quickly. What I want you to do, and how it has to be done if you're going to learn how to do this, and there's no shortcut. This is practice. This is muscle memory in terms of learning stats. When we are working through the problem, I'm expecting you to do all the little steps in between. So if there's a big data set, there'll be some big data sets, some small data sets, and the step is square the column and then add everything up. I don't want you to be, oh, I know how to square, I know how to add, so I'm just going to look at the answer on the next slide and just use that going forward. 90% of the mistakes that happen, not 90, 80% of the mistakes that happen in these early stages of squaring, adding, and the very front end of a problem. You need to work this out because I need you to figure out if you have a carelessness issue, if you have an impulsivity issue, if you are reckless. There are going to be some dumb mistakes that happen to everybody. Everybody is going to have that happen. But if it's a common problem, working through these and seeing that you keep making mistakes and adding, or you're getting the columns wrong, problem after problem, that's an issue we have to fix. So the only way you're going to know that is if you actually work through these things together. So I need you to do the work as we're doing this. Again, just like you would be doing if this was in class. But pay attention to where the errors are if they are coming. And if you really notice it's happening in the same place every time, you're going to be surprised it's really in that sort of first portion. The simple stuff is where most of the issues come up. We want to fix that, because if you make a mistake in the very beginning, those numbers carry through every other step, and that will sort of knock your point total down. The second thing we're going to have, and each time we have an exam, afterwards we have a brand new thing we're going to have to worry about. The thing we're going to have to worry about now is multiple versions of the same formula. So we are learning 3 different kinds of correlations. So in the question right up, there'll be a set of data that you'll look at, and there'll be a blurb up top that sort of describes what is going on. And the last sentence will be something like, what is the relationship between X and Y? Or conduct a correlation and determine R value. Now, that doesn't tell you which of the 3 formulas to use. That depends on you. So what we're adding now is going to be choice in the matter. Which test you choose to use is going to be a big part of how well you're doing. So we need to choose the right test for the set of data that we have, and the questions in some cases that we have. So be aware of that. We're going to start that starting today. After exam 2, we're going to be getting into statistical significance. We're also, I'm sorry, I should also mention, we're also going to be doing a little bit with interpretation. It's a little bit weak to start with. We'll get it stronger. But these are things that we're adding on. So from this point forward, we're going to solve for something. You're going to have chosen the right formula, and you are going to have to make an interpretation about the finding. That's true of everything that we do from now on. After exam 2, we're going to be introducing statistical significance, and that changes things. And after exam 3, we'll be adding a little bit more to that. So one new step is added each of these big chunks after each exam, and this is what we're going to have for today. So I hope you have all your stuff ready. If not, stop here, go print them out, and then come back when you are ready to go. Okay, now this is part of the thing that I took out of the actual lecture and sort of put with the formula and worked through. I have my mouse upside down, which is why I've been having some problems. I've mentioned these damn animals and these damn cartoons, and this is, of course, General Information Fox. We'll deal with this crap at some point. I've sort of mentioned that I'm not thrilled they're here, but if they work out, I'm going to have to acknowledge that I'm completely wrong, and a 9-year-old child who comes from the pits of hell is correct. General Information Fox shows up to give us general information. So apparently this is going to make a big deal in your learning, at least according to the 9-year-old. So when you see them, general stuff is being provided. So I want to cover the assumptions, and this is part of what you're going to use to determine whether or not the Pearson is the appropriate statistic for you to be using. Truly, only one of them is sort of necessary now. Everything else is sort of an expectation that it's going to be this way. Our data sets aren't big enough to worry about these other things, and that's just part and parcel of learning how to do something. So this is theoretically the things you're going to check for. We're really just going to be focusing on one, and this is going to be the type of data that we have. But let's run through these really quickly. The assumptions, and this is truly not just an assumption of the Pearson, it's an assumption of anything classified as a parametric statistic. Parametric statistics simply means that we are sort of operating in a mathematical realm. We have expectations that there's a normal curve, we have expectations about what having a normal curve means, and expectations about how math is going to work within it. When we get to the non-parametric test, we don't have those assumptions about there being a normal curve. We don't have assumptions that we're going to treat this math-like, find out what we do. It's a very different set of procedures. But what we do have is just that understanding that it's going to be parametric or non-parametric. If it's parametric, most of these are going to be true for all of them, okay? If it's not true, non-parametric, we're not going to assume that these are all true. So data is linear is one we would expect of any parametric statistic. Second one, data is normally distributed. Okay, it's a normal curve. Again, true of the parametric statistics across the board. Data is continuous. That is also tied in with parametric statistics. And it leads us to have the idea that this data that we're having, or the data that's showing up, is going to be interval or ratio data. So again, why we started with the nominal ordinal interval ratio is because that is now a decision point. That is where we make a decision of what correlation, in this case, we're going to be using. If you have interval or ratio data, statistically, we're going to treat them the exact same way. There's no distinction between those two. But if we had ordinal data, if we had nominal data, we would be limited in either the kind of correlation we can do, or if we could do a correlation at all. All right, so the kind of data you had in the data set is going to be important for us going forward. So be able to recognize interval or ratio data. So above ranking, this is actually consistency on the scale between the data points, and that's what we're going to be looking for. So interval or ratio scale means we're going to be doing the Pearson. If it's something other, we're going to be talking about the other options. Homogeneity of variance, again, that's how things are spread out in terms of the error. Normal distribution is sort of taking care of most of this. Correlations are about a relationship. If you remember back to the set of notes on what correlations are, we're going to be measuring mathematically how changing one variable causes a change in the other variable. So as one set of data, the scores start to rise, what happens to the other data set? If they're both moving in the same direction, okay, as one goes up, the other goes up, or if one goes down, the other goes down, we classify all of those as positive correlations. They're moving in the same direction. And the idea is that we will analyze that or interpret that in one particular fashion. If we have a situation where as the data goes up on one scale, so as data goes up on X, the data goes down on Y, or opposite, we will see that that would be a negative correlation, and we would have to interpret it differently, whether it's a positive or negative value. In correlations, the positive or negative sign doesn't mean plus or minus mathematically, it means direction, left side or right side. The positive values off to the right, the negative values off to the left, but it really is just directional. It doesn't connect to the actual numeric value. The numeric value, of course, has to follow or fall between the values of 0 and 1. Okay, 1.0, that is between 0% and 100%. Anytime you calculate a correlation, if you get a raw score higher than 1.0, unless there's a weird rounding error and you get like 1.01, okay, that actually can't happen. But if you get a value of like 3, you've done the math wrong and you have to redo it. All right, so those are things that you look for. What I have down here as well at the bottom is a rough idea of how strong correlations are. And we tend to just talk about it, at least correlational data, for the reasons explained in the set of notes. This is really about as far as we're going to go in terms of making claims about statistical significance. I mean, we could do it, but most people, this list is going to be here. So I provide this here, and it's provided several other places. If you're trying to interpret this, refer back to this list to sort of see how you would characterize this. Remember, the correlation coefficient, we're actually interpreting this as the absolute value. So if it's positive or negative, 0.70 to 1.0, positive or negative, those are both very strong. Weak is close to 0, strong is away from 0. Okay? So when you're interpreting in terms of strength, the strength is just a numeric value. We interpret the absolute value, which is the number alone. We don't look at the positive or negative sign, which is, again, just a directional thing for us. Okay, so here's the data set. And again, notice we're working with small data sets, so I'm expecting you to do this. And there's not really a large setup for these, so I'll give a little something. I didn't mean to make these hard. I didn't want to take up space. But here's our first data set. So we have two sets of data. We have an X and a Y. Correlation is always correlating two columns of data, which means if I had out here, this could be subject number. So one person gives two scores. If you think back to that scatter plot, one person has an X value, that same person has a Y value. The thing that shows up on the chart is the intersection of their X and Y. So we have two scales here, but one person is providing two scores. In other situations, every data point will refer to a specific individual, but not with correlations. Correlations have each person, this is person 1, has this self-esteem score and this GPA, this X and this Y. Now, this is a self-esteem and GPA correlation. So if I had a setup for this, it would be a person takes a test, they're given a value of self-esteem. They can go from, technically can go from any range I want. Looks like this scale is going to go from 0 to 10. You can interpret it, again, this would be provided in the actual write-up. I would assume that higher scores mean higher levels of self-esteem, so the closer to 10, the higher the self-esteem. Closer to 0, the lower the self-esteem. And then you have a GPA, which works like GPAs do. Now, remember that we have to determine if these are interval or ratio, because if they are, then we're doing a Pearson. If it's something else, we're not. So we have to make sure that these aren't ranks. And we know the GPA is not ranked. That's ratio data. You can have a 0.0 data point or GPA, and that means that you have flunked everything. Okay, so that's a real number. So we certainly know GPA is a ratio scale. Self-esteem here, a scale from 0 to 10 or 0 to 100. This is an interval scale data. Okay, this isn't a ranking. There's not ranked. You could have, look at this. Two people have the same score. That means that they both have an equivalent level of self-esteem. This is measured, but they're not being ranked in order. This is a measurement of. Okay, so that makes it interval data. So we know that both of these scales are interval and ratio. Therefore, we're going to go ahead and do a Pearson. If one of these was not interval or ratio, we would do something else. Okay, but both scales are interval ratio. Therefore, we go forward with the Pearson. Again, we're going to be doing this step by step. So explainator. Just let me get my head around this. It's important to do this because you lost the bet. Explainator. Okay. All right. My manhood is still intact. I'm still an adult. No one can take my PhD away from me at this point. Cartoon animals are cool. All right. Okay. Sorry, just needed a moment to collect myself. It's out of character for this to be there. Okay, so explainator is there probably to explain stuff. He's going to tell us what to do. I'm also going to use color coding, which also works, but apparently cartoon animals really make the difference. So we're going to walk through step by step. And step 1 is sum up the X and the Y columns. And again, every analysis that we do, I am breaking it down step by step, so I'm not going to lose anybody. So what I want you to do, if you've not been doing this, I was trying to give you a little bit of time with me, complaining about the animal figure to add this up. If you haven't done that yet, pause, sum these two columns up, and then come back and then go on to the next step. Okay, now the next step here, and I'll just sort of show you, I'll move the picture out of frame. This is always going to be in the way today, but I think it might be better over here. I'm just showing you the first time through. I won't do this every time, but this is the first time we have an X and Y column, so I thought I should at least do something. I'll explain how you know that these are the columns that we need to calculate. But what we're going to do for an XY column, if you're unfamiliar with it, is each value of X multiplied by the corresponding value of Y. So our X value is for this first participant, their self-esteem is a value of 4 multiplied by the GPA of 3.0. Because this has a decimal point, we want to make sure that there's a decimal point here as well. 4 times 3.0 is 12.0. That's what X and Y, X multiplied by Y for each of the values. We have an X squared column, so for every value of X, 4 squared is equal to 16. And we have a Y squared column, 3.0 squared. This should be 9.0 if I'm keeping up with this, but I've fallen apart on our first example. 3.0 squared is 9.0. So you can sort of see from this, I'm asking you to create and sum the columns of X, Y, X squared, and Y squared. So fill out all the green bubbles here, and then I'll sort of show you where you would have known to do that, how you would have known that these were the columns to do. So fill out all the green squares, do the math that's required, then sum each column up, and then come back and check your answers. And then when you're done, unpause. Okay, again, double check all the way through here and make sure that there were no math errors. Now, I left this column blank, and this would normally be where we have something called subject number. This would be subject 1, subject 2, subject 3, subject 4, subject 5, to help us identify that one line is for, there's 2 scores for that person. That's going to be known by us as the idiot column, and you'll see why as we go through the lab example. I think I sort of have this phased in. But here are the answers that you should have. You should sum at the XY column, have a value of 48.10. Sum of the X squared column should be 63. Sum of the Y squared column, 41.25. So these columns down here, ones that are in bold, these are the things that we're going to use as we go forward. Okay? All of this work needs to be done, but it's the outcome of those columns, the sums of the columns, which we're going to be using in the formulas itself. All right. Make sure all those are correct. And if they are correct, fine, you can go to the next stop. If they're not correct, pause, go back and figure out where the mistake was, change it, add them again, and make sure you have these numbers before you go forward. Okay, now here is the first of the formulas, and this is, again, you heard me say that the standard deviation really didn't even feel like a formula, it was so small. This is the first one, which if you're math phobic, this one you're going to be breathing a little bit more intensely, because this looks like a formula. It's extraordinarily simple though. Just don't psych yourself out for it. Now, the last slide we had, I had this up here and I said, just calculate these columns. Well, how would you know to calculate those columns? Let's say that if you've done the Pearson a number of times, you just know what to do. You don't have to really think about it anymore. But let's say it's exam day and you have that moment of like, oh, fuck, I forgot everything. I don't know what to do. You have that weird like flop sweat that's going to happen. You are extraordinarily cold and sweating, and you know it's all going wrong. Calm down, calm down. There are ways out of this. Again, this is, you can't predict who it's going to happen to. But these things do happen in stats class more than other places. So this flop sweat is going to happen, at least to most of you, sometime during the semester. When in doubt, if you truly just blank, first off, take a moment, because if you're freaked out, you're not going to be able to do anything. So calm yourself a bit, do some breathing, and then come back. And the step that I always start with, although I did it backwards this time, is write the formula down. You should have been able to tell that this was a Pearson. Step 1, because you get a point for it, or eventually you get a point taken off if it's not there. The first thing on your homework, the first thing whenever you solve this, is writing the formula down. So here is the Pearson formula, and I'll walk through it and then we'll go back and explain how you read from this. N is multiplied by the sum of the xy. Subtract from that the quantity sum of x multiplied by sum of y. All of that is over the square root of, bracket 1, n times the sum of the x squared minus sum of x quantity squared, close bracket, second bracket, n multiplied by sum of the y squares minus sum of y quantity squared. So how you would solve this is you solve within the brackets first. So you solve these two things first, then go up and do all the multiplication and division. So you solve this, subtract this quantity from this, so multiply those two and subtract the quantity from this. Have this solved, take the square root, divide the bottom from the top. Now, writing the formula out tells you what columns you have to calculate. Notice in here it says sum of the xy. Well, sum means it's going to be a column, and I need that final answer here. So I know that I'm going to need to do an xy column. That's why I put xy first rather than x squared or y squared, which would probably be how I would have done it normally. But xy is the first sign, the first column that I'm going to need to calculate. It's right here. I know that by looking at the formula. Minus sum of x. I have an x column. I know the sum of that column is what I'm looking for. So that's here. So if I didn't know it, I would just have to sum up this column. Sum of y. Okay, here's my y column, sum it up. That value is going to be important. Then down at the bottom, ignoring the other things for just a moment, n, which we'll get to in a bit, multiplied by the sum of the x squares. This means I have to calculate an x squared column. So I have to square everything, sum it up. Okay, sum of x, have that quantity squared. And the same thing for the y column. So by just calming down and writing the formula out and looking at the formula, I know what columns that I'm going to need to calculate. And I can do that. And if you're nervous, things like simple addition, simple squaring, simple multiplication may actually calm you down. You also can make mistakes in it, but for most of us, it's going to calm us down. I know what 2 squared is. I didn't even need a calculator. And that may be enough for me to sort of feel a little bit safer about what I'm doing. So I would always say this is truly step 1, but I'm doing this in order. And this is the first one we're doing. I wanted to walk you through the columns itself first. So that's why this is a little bit different in order. All right, notice the other thing that's here, and this is right here. N here refers to pairs of scores, not individual scores. And that is going to differ from formula to formula. Whenever you have one person giving 2 scores, it's going to be here with correlation. It's really true of all the correlations. It's going to be in the correlated t-test or the dependent t-test, as we'll learn both names sort of work. Whenever you have something where one person is giving multiple scores, N tends to refer to pairs of scores. This really is, N is trying to get sort of a head count. How many people actually took part here? If a person only gives 1 data point, okay, and you've got X's and Y's, that means if they only gave 1 data point, those have to be 2 different people. Here, if it's a correlation, that means that this one person gave both scores. We'll get to the reason why when we get to t-test. Okay, that's conversation for later, but understand now that N means pairs of scores. All right, that was different when we did standard deviation. N is going to be different when we do most of the other tests. But for things that are correlated, where there are 2 scores per person, it is going to respond to pairs of scores. Okay, so we write our formula out, then we would have solved all the columns. Then our next step would be right here, plug this into the Pearson R. So the first thing we would have is N, number of pairs of scores. So how many people do we have? 1, 2, 3, 4, 5. So N is equal to 5. Sum of the XY, 48.10, minus sum of X, 17, minus, or multiplied by sum of Y, 13.9, and then fill the things in on the bottom. So go ahead and finish filling everything in with the right columns, and then we're going to go back and make sure you have those all right before we solve. The next slide will have the correct answers. One other thing that I want to mention, this bottom portion down here in each of these brackets should already seem familiar to you. Now, it's unusual because we have both an X and a Y, but we have heard sum of X squares, sum of the X squares minus sum of X squared. Remember, that's the sum of squares thing that we were just working on. So that's why I said learning the formula that I had shown you in the video for standard deviation really is the better way to go. I will say from looking at the homework and looking at the exam, not completely graded, they're getting there. Some of you are still using the other formula, the old way of doing it. You can use either one, they both get you there. Please, for the 1 or 2 of you who are using the formula that I did not recommend, please start using the one that I gave you in class. It will save you a ton of time in the future because you can start seeing that you're used to sort of solving for sum of squares. Okay, so that's my last time I'm going to beg for that. If you want to take a lot more time to do something, knock yourself out. You don't get any extra time on the exam. That 3-hour window is a 3-hour window. It's not 3 hours plus extra time because you're choosing the inefficient way of doing things. Okay, so plug everything in here and then come back. Okay, so this is what you should have. 5 multiplied by 48.1. And truthfully, as long as we're not doing the addition and subtraction, you can sort of have another step here. I'm not requiring it, but you could solve each of these mini equations and put those answers over here. So 5 times 48.10 minus the quantity 17 times 13.9. All of that is over. Solve in brackets first. 5 times 63 minus 17 squared, and bracket. 5 times 41.25 minus the quantity 13.9 squared. Solve both of those within the brackets. Multiply this bracket value by this bracket value. Then take the square root of all of that, and then divide the top by the bottom. All right? So next step is solve. Okay, so just follow the steps that I've just said. Again, pause it here, solve, and then we'll see if you have the right answer. Okay, so here I did the simple, or the next step. Again, this one, as long as the numbers are in the right places, the math shouldn't go wrong. So this is for those individuals. And again, I would say on complex formulas, this is sometimes useful to do. You don't have to do this particular step when you're showing the work. The last step needs to be that you write it down, have all the numbers plugged in. I need to see all the work in the table up front. If you went from the last slide just to the answer, that would still be fine. I do recommend, if you are wanting to make sure and you want, so if you make a mistake and you don't know where you made it, sometimes it's hard to find it. This sort of intermediate step may also be useful for you. So I personally recommend doing it, but it's not going to be part of the grading. All right. So if it's not there, you're not getting points off, but I think this could help a good chunk of you. All right. So here should be what you have. When we solve for the top, it should be 4.20. We solve at least within the brackets, value of 26 multiplied by 13.4, take the square root, and then do division. Okay. If you've done that step and have a final answer, you can go to the next one. If not, solve for this, obviously pausing, and then come back and join us when you have the full answer. Okay, so the final answer here, and again, this will be in decimal points. Remember that values of correlations always between 0.00 and 1.00, 0% and 100%. We're going to have a decimal point as our value. Now, we do have to write out the final answer. Now, how will I know something is a final answer? Well, we're going to have at least one little step up front, and we'll be expanding on this as we get into the t-test. We haven't learned about degrees of freedom yet. That's coming after exam 2. For now, we're just going to identify it with the correct term and list it. Now, I would say in general, so I spoke to Sammy, and Sammy's comment was, after scanning stuff and sending them to me, she said, I understand now why you professors get so angry, because she could not read, several of you could not read your handwriting. I've done this many years. I'm used to this. Sammy was a little surprised at how messy her classmates are. Just saying, she's throwing shade. Already she's throwing shade. But I've also seen your handwriting. She's got a point. Some of you, maybe English language is not your foreign, or is not your actual tongue. You speak in Sanskrit, because those numbers are some weird combination of animal, mineral, and vegetable and numbers, as far as I can tell. So as long as I can figure it out, we're fine. If you get sort of a snotty email from me like, what the hell, man, you're going to have to clean it up a little bit. So just be aware that that's probably going to happen for some of you this semester. All right, we solve it. Our answer should be R, and R is a symbol for a Pearson. So when you have a lowercase r here, and it's always lowercase r means it's a Pearson correlation. So when I look at this, I know what formula you use. I could have known it by looking up here in the formula you wrote down, but I also know it by here. So you have to identify the value by the test it was, that test it came from. So lowercase r means it's a Pearson. R is equal to 0.2281. Now, in general, we should always put on the pluses or minuses. In practice, if it doesn't have any sign with it, indicates it's a positive. But I would, again, get into the practice of doing it the right way. This should be positive 0.2281. I carry this out. You can't really see it here, but I carried, actually, when I did the calculations out to 2 decimal places, I actually carried it out to 3, but yeah, I just didn't want to put in the PowerPoint to get to this. So there might be some rounding error off here. Your value may be a little bit off at the very end. If you're off by a couple thousandths of a point, I really am not going to worry. It's when you do the bad rounding and it shows up in the first two values is going to be here. Now, why did I actually carry this out to 4 points? Okay, first off, you do not have to change this. This is a correct answer. This is a correct final answer. R is equal to positive 0.2281. That's your final answer. Or if you just carried it out to 2 places, you would have to round up. So R is equal to 0.23, rounding up that 2 because the 8 follows. That would have been okay as well. The reason I carried it out to 4 positions is students sometimes feel more comfortable turning this into percentages. And in percentages, you multiply by 100. So you move the decimal place over 2. 0.2281 really is 22.81%. So I carried out to 4 decimal places when I solve things minimum for correlations, mainly in case students want me to turn them into percentiles. Either way is correct. Some people just like the idea of percents better than decimal points. Either one is absolutely correct. Any of those options were correct. If you did not get that, you have to go back and solve again. All right, you have to go back and figure out where the error is. This is what happens when I have to score your data, when I score your exams and homework. If the numbers are wrong, I have to go back and figure out where something went wrong to show it to you. That's why I need it to be a little bit readable. And I'm not jumping over 14 pages following arrows and, ignore this, go to point A to find the next part of the answer. I'm trying to help you by figuring out where something went wrong. If you make it hard on me, I'm not going to want to help you. So again, if you are one of the messy people, do better. Okay, don't be perfect, do better. Okay, so whatever we call this box, where it's introducing a general point, really isn't something we want to worry about now. We are going to come back later when we hit the T-test, which is after exam 2, and we're going to be doing a little bit more sprucing up of where this R is. We're going to be adding something called degrees of freedom. Again, I at least mentioned that before in passing. And we're going to be talking about statistical significance. At this point, I don't want to throw everything at you at once. So we're taking these things in step. So understand we're going to be going back to this and changing this up. But for correlations, just the R to identify what correlation it is and the value, all I need, okay, for a correct answer. Would be nice if you circle it so I can find it. Because some of you cram things into the corner of a page rather than wasting a page of paper. Again, I need to find it, is something to be thinking about. Okay, so we'll come back to adding to that, but for correlation, that's going to be just fine. So here would be a final answer. Notice on my final answer, I did put the positive sign in when you do it. Now, if you flip back to the original slide or go back in the video feedback to that original slide, it sort of said, here's what the different strengths of correlations are. And 22% or 0.221 or 2281, excuse me, comes with the sort of description of weak. So this is only a weak positive relationship. Again, the positive sign telling us is the X score is going up, the Y score is going up, or the X score is going down, the Y score is going down. They're moving in the same direction. That's what positive tells us. But this is a weak correlation. So both the positive or negative sign and the value tells us something. There is a weak relationship between someone's self-esteem level and their GPA. That is sort of making sense of the value. Now, notice I also said in the lead up to this that I want you to interpret this. And I want you to make sense of this. So you described it, and that's really what you did is describe. You didn't interpret it. If all you did was say there's a weak positive relationship, I knew that just by seeing this and this. This is just this stated into words. That's not an interpretation, that's a description. To interpret something, you have to go back to the question itself. This is a analysis on the relationship between someone's self-esteem score and their GPA. An interpretation requires that you go back to those terms and make sense of this. Now, I know that it's a weak positive relationship. Positive means that they're changing in the same direction. Weak is based on that numeric value. So an interpretation would be something like this. And the reason I'm doing this is to show you I'm not expecting something super complex. I just want you to sort of tie it all together. So what this means, what a positive 0.2281 correlation means between self-esteem and GPA, as someone's self-esteem score increases, there is a slight corresponding increase in their GPA score. That's the interpretation. I just took the stuff and went back. I incorporated the direction. As one increases, the other's increasing. That takes care of the positive. And the idea slight is sort of a nice phrase to use for a weak one, if I didn't want to say it was a weak correlation. There's a slight change in the scores from X to Y. If you have strong ones, you can be stronger in your interpretation. If it's near 0, you have to be even weaker than this in interpreting this. There's no relationship between these two. There's this one, there's a slight one. There's not much of one there, but there is something. Okay, that's what the interpretation is. Okay, now hopefully you're with me the entire way there. That is your first real formula for this class. Congratulations, you have done your first Pearson R, and congratulations on that. Doesn't mean we're done, but it means we're done with the first one. So this would be the time to take a break, pause, go get something to eat, go slap your roommate if she's misbehaving, making too much noise, go listen to some music, come back, and we've got some more for you. All right, welcome back. Hope your roommate was behaving themselves. Not mentioned in the Sweetbriar Pledge, but I think it's implied we're not supposed to be smacking our roommates. So I don't think you listen to me, but you know, sometimes you just need to reset with her sometimes. Ugh, ugh. You're the best person in that room, is all I'm saying. Your roommate kind of sucky. Unless she's also in the class, in which case you're both equally wonderful. All right, our next correlation is something called the Spearman row. All right, all three of these are correlations. Pearson R is the most common. Here is for when we have a different kind of situation. So the Spearman row is the second of our correlations. And once again, my ugly face is in the way. Let's cover that damn fox up. I did at least choose a fox. I may have been pissy about having to do the cartoon animals in here, but I did at least pick a fox. So you're welcome. You're welcome, Vixens. I care. All right. Now, Spearman row is something called, in truth, the Spearman rank order correlation. You should take a hint there that rank means something. So this is going to be something where data is ranked. It's going to be on the ordinal scale. Now, there is one tricky thing about this one, and none of these things when I say they're tricky, they're not really tricky. You just have to remember them. But remember, I am providing you the formulas on exam day. You don't have to memorize the formulas. Over time, you should know how to do the sum of squares and standard deviation and mean by memory. You should know that. For heaven's sake, you should do that. But the rest of these formulas, I don't expect you to have any of these things memorized. I will provide those for you. When you're doing homework, yeah, look them up. That's how this stuff is done. However, there is sometimes some extra things, and it typically is common with the non-parametric. Whenever there's something labeled non-parametric, or you know it's a non-parametric test, that means there's some sort of weird little addition that we have to do. I will provide you the formula. It's not going to remind you. Having that formula down is not going to remind you to do this step. So you do have to memorize these little things as we go forward. Okay, we are going to use the Spearman rank when one of the data columns or both of the data columns are ordinal. We have to have ordinal data in at least one of those two columns. And again, remember that ordinal data is ranked data. Okay, so one of the columns of data must be rank ordering rather than interval ratio data. If both of them are interval ratio, and you could have one that's interval and one that's ratio as we did last time, as long as they meet at least interval for both of them, we go and do the Pearson. If we have at least one of them being ordinal, the other one having to be ordinal, interval, or ratio, can't have nominal data and do correlations. We'll show you what you have to do if that situation arises. But at least the other one is at least ordinal. So one is clearly ordinal, the other can be ordinal, interval, or ratio. We're going to go ahead and use the Spearman row. Now, here's that little point that you have to do. So first off, recognize the data tells you which of the correlations to do. Then the little tricky point. If one of the data points is ordinal, and the other one, in this case, we're going to have is either interval or ratio, what you have to do is transform that second data column, the one that is interval or ratio, into an ordinal column as well. So you're going to have to make a transformation of the data from its original form into its ordinal form. And again, we'll go through this with the first example. If both of them are ordinal, you don't have to worry about it. If either one is nominal, you're not using the Spearman row. If both of them are integral ratio, you're using a Pearson. So at least one column ordinal, the other column has to be at least ordinal. But if it's interval ratio, you have to go through and rank that column, turn it into ranked data. Okay, so as a result, the Spearman row does a correlation looking at the relationship between two ranked variables. And again, they may not have started out both of them being ranked, but by the time we get to them, both of them are ranked at the end. So we're looking at ranked data now. Spearman row is better if we have nonlinear data. If we violate the process of linearity, we turn them into, we have a non-normal data set. You sometimes want to turn them into a different scale and analyze them non-parametrically. So we could take just the messed up data set violating the linearity rule and turn it into ranked data and analyze it using the Spearman row. There are reasons to do that. There's arguments for and arguments against doing it. The non-parametrics are generally weaker and you have less confidence in them as compared to the parametric data. But if it's the data you have, that's how we're going to analyze it. Okay, so every analysis, strength and weakness, is going to be there. Okay, in this example, we're going to be working with an athletic coach, and what she has done is ranked her athletes according to their speed and their overall endurance. So she had them run a race, whatever their actual times were, she turned them into the fastest, the next fastest, the next fastest. So 1, 2, 3, 4, 5, 6 from lowest to highest, and their overall endurance, made them keep running until they dropped or quit, and then rank their endurance that way. However it was measured, these are ranked data. Okay, so here are the rankings. Now notice the rankings, also something that I didn't mention, but the rankings can go in either direction. For this particular data set, I have 1 being the best and 6 being the worst. So 1 is, if this is speed, 1 is the quickest, 6 is the slowest. If this second one is Y is endurance, 1 has the best endurance, 6 has the worst endurance. Now, it doesn't matter which way you do that. Some people prefer ranking it in the opposite direction. Mathematically, the only thing that's going to happen if you rank it differently than I do is that instead of having a positive correlation, you'll have a negative correlation. And that changes how you interpret it, because your scale, as it goes up, by ranking it the other way, my scores are going down. So you actually, the only thing that's going to change is the positive or negative value. You'll have the exact same mathematical value. So you just have to interpret it differently, because my 1 means best, and your 1 could have meant worst. All right, so I would have a positive value, you would have a negative value. We just interpret it differently. So pick the way that you do and then go. Now, for me, generally, 1 is always the lowest score in the analysis, and whatever is going up is the highest. That's just generally the way that I do it. It doesn't matter. Whichever way you do it, you just have to know that that's how you rank them and use that in your interpretation of the data. Now, in this case, both of these things are ranked. In the lab, you're going to have to do a transformation of this. But for the first time through, I just didn't want to bother with that. So both of these columns are ranked. However, if this first column, let's see X, if this had been presented in milliseconds, for example, and this one was presented as ranking, we would have had to re-rank them. And once we re-rank them and turn them into a normal scale, we don't use the raw data anymore. Once it's transformed, we just use the ranking. So by the time you sit down to the analysis, both of them had better be ordinal. However they started out is not going to be there. If you don't do that and then you solve it, you'll get something like an R value of 47.6. Okay, that's 4,700%. You know that that's above 1. 47 is greater than 1. Something went wrong. Don't be looking at the math. You just didn't turn it into ordinal data. So the numeric value is going to explode if you have made a mistake. So when we have Spearman row, both columns have to be ranked by the time you start the analysis. Okay, so we have our X and our Y. And notice in this example, as promised, I have the idiot column. Okay, and I say idiot with the most love in my heart because all people have done this at some point. But again, this just means, as a reminder, subject 1, first participant, has a speed ranking of 3, endurance ranking of 5. Second person, known as one of the top stars of the team, has the quickest speed and the second best endurance. Okay, and then the second best speed for number 3 with the first best endurance, and so on. Here are their rankings. One line equals one participant. Now, I'm going to leave this up here to show you why I call it the idiot curve and that you will make this mistake. Brain farts are going to happen. They happen in homework. They happen in exams. Sometimes you catch them, sometimes you don't. But just acknowledge there are going to be some dumb mistakes that happen. They are just going to happen. Do not berate yourself for them. Okay, step 1. Okay. And actually, we're starting with step 0. Make sure both columns of data are ordinal. If not, rank the data columns so that they are. All right. We've already done that. This one is presented in ranked data, so technically this is a step, but in this case, this is actually step 0. Now, I did grade this out to identify that this is the subject column. This just means this line is subject 1. This line going across is subject 2. This is subject 3. Now, it's going to turn back to white probably in our next slide, because I didn't go through every data slide and turn this, but just remember, if I'm saying the subject column or if I say the idiot column, this is a column I'm referring to, just to show you the kind of mistakes that will get made by everybody at some point this semester. And just accept that it happens and move on when it does. Okay, step 1. Well, apparently I'm not going to let you get to step 1. I put this here because this formula is a little bit unusual. So I actually moved this slide up right before I started taping. I forgot completely about doing this. So I should have, step 1 is sort of what comes next. Step 1 is look at the formula, but this formula had some extra stuff in it, so I wanted to get it all up on the first slide. Here's our Spearman row formula. R sub row, so sub just means it's sort of lower than. This tells us that R means it's a correlation. Now, R by itself means that it's a Pearson. We don't add anything to it when it's a Pearson, but if it's a not Pearson, we do add something. So when you are solving for a Spearman row, your final answer should be lowercase r for correlation, sub row. This is the abbreviation for Spearman rank order formula. This is a formula. Okay, so r sub row is equal to 1 minus, and then on top of the fraction, 6 multiplied by the sum of the d squares, divided by n multiplied by n squared plus 1. Now, a few things about this formula. Again, remember they're being provided for you, so you don't need to memorize this, but this is what the formula looks like. Now, this formula has some constants in it, and this is important to recognize, and if you need to make a little note, do that. Our data set sometimes might have 6 people in it, so there's going to be a number of 6s in here. This 6 is a constant in the formula. If we have 6 participants, if we have 20 participants, if we have 1,000,000 participants, this would still be 6. This is still 1. That is still 1. This is the formula. The 6 and the 1s are there are constants. They're always going to be 6 and 1s no matter what else is going on. Okay? That only gets confusing if we have 6 participants, because then these may also end up looking like they're 6s. Okay, that first 6 has nothing to do with the number of subjects. This 6 is a constant. Okay? So, our number of pairs of scores are 6. But the 1 and the 6 and that 1 are constants. D, we haven't run across the D yet. D stands for a difference column. A difference column is just value of x, subtract from it the value of y. So x minus y will give you a different score. Okay, now we look at this. What do we have to do? Well, we need at least D, but it's D squared. So we're going to have to solve for D. Then we're going to have to square D. So we're going to solve a difference column, make a difference column. We're going to square the value. And then we're going to need to sum up the D squares. Okay, notice that this is all in the parentheses, sum of the D squares. So technically, we don't need to sum up the D column. We're going to have it, but we don't need to sum it up. We need to sum up the D squared column. So adding up the D column by itself is an extra step that you don't have to do. We also need to figure out what n is, and n is the number of pairs of scores. In our case, n is going to be 6. All right, so here's our data. And I did the first one for us because it is the first time that we have a different score. I went ahead and sort of just did the simple math. I showed you where the math comes from. Now, D difference is equal to x minus y. Our x value for participant 1 is 3. Our y value for participant 1 is 5. 3 minus 5 is equal to -2. Now, in this one, it kind of ends up not mattering, but in other ones it will. So whenever you're doing a difference column, yes, the negative and positive signs are going to matter, okay? This is a different score in a non-parametric test. We're going to have some different scores in parametric tests, and we're going to need those positive and negative signs, okay, for them. This one, it ends up, we're not going to end up using it, but still, whenever there's a different score, positive and negative values, just do it the correct way, all right? And even for some other ones, the positive and negative scores is important for other reasons, so always include them here. 3 minus 5 is equal to -2. The next one, of course, participant 2, 1 is our value of x, -2, and you solve and put it here. And then do the same. And notice that I just have down to here. At this point, I don't have a sum up because we're not going to be summing things for this column, okay? So just solve to this point, solve for those, and go ahead and fill these green things out, and then pause, obviously, fill those things out. When you have all of that, go back or go on to the next slide when you're ready. Okay, before I get to the answer of this one, I do want to mention, because the idiot column may have been used. This is how the data is going to look on your sheet of paper. If you are stressed, if you are anxious, what is a common mistake that you might do? And here we're going to be solving a difference column, value of x minus value of y. Now, doesn't mean you're going to do it on every single one of these, but on one of these, you might actually have gone, instead of x2 minus a y of 1, you actually went subject number 3 minus an x of 2, or subject number 3 minus y value of 1. You went back to this column by accident. You just quickly looked over, saw 3, and solved for D. Those are numbers. They don't disappear. So that means that it is possible you're going to be using the wrong column. Value of x minus value of y. So always, if you have a difference column, make sure you didn't do that. Okay? That's why we call it the idiot column. You're an idiot for using subject number as a piece of data. It's an identifier. If this was labeled subject A, B, C, D, E, and F, it would have been a difference, so you wouldn't have done it. But because it's subject 1, 2, 3, 4, 5, or 6, one time this semester, everybody is going to subtract from subject number by accident, okay? And it's going to screw everything up. All right, so again, make sure that you're not doing that. So you can certainly, on exam or homework, cross subject number out, cross that column out, if you find yourself likely to make that mistake. Remember that if one of these columns was an actual interval or ratio data, you would have had to re-rank that. Make sure you're not using the raw score column for something that was interval or ratio. You're going to be using the ranked score column for that. So this is a prime place where you're going to have some clutter on this, and you want to make sure you're using the right numbers. I know you can add and subtract. In this case, I know simple subtraction is completely within your capacity. However, having extra numbers up there plus stress or plus carelessness mean that some mistakes are going to fall into this. That's why I want you to do this. If you see yourself prone to those mistakes, you need to know that on homework and exam, you need to be real careful on those kinds of problems. And the only way you're going to know that is if you're actually solving this and not just waiting for the answers to come out and saying, oh yeah, I know how to do this, all right? If you're not doing the work, do not be surprised that you end up with a low grade. It happens every single time. Okay, and I get a reminder that you can have the negative values. Okay, step 2, we're going to create the difference squared column. Okay, so I now have a D squared column. So I'm going to take my value, in this case, of -2 squared. Remember, by squaring, we're getting rid of the negative values. So this one works itself out regardless, because we don't really care about the D column. We just care about the D squared column. So square each of the values in the D. Write their values here. We also need, in step 3, to sum the D squared column. So solve for the light colored greens, solve for the darker colored greens, and when you are done with that, so pause, and then when you're done for that, come back and check your answer. All right, let's make sure we have the right answer. And in this case, again, positive or negative 2 squared is 4, the 1's squared are 1, and the 0 squared are 0. So adding those up should not have been difficult. We have a D squared column score of 10. Okay, now that's in red. That's because that's the thing that's going to travel with us into the formula. So I'm going to pop the formula back up. We've already seen this, so this isn't a new step. But because the way, again, I just threw that up there right before taping, so this is still listed as number 4. I write the formula down typically as stage 1. When I know what kind of formula to do, I write the formula down. This told me what columns that I needed to add. That's why I put it normally as step 1. But in the order that we're doing this, this is the 4th step, the way that we're taking this apart in training. So remember, the 6 here is a constant, the 1 here and the 1 here are constants. Okay? We have the sum of the d squares, d squared, sum of d squared is 10, n, number of participants, not number of scores, number of participants. In this case, our n is going to be 6. So we're going to have a 6 here and a 6 squared there. Plug those in, and you should have this. Now, again, I use this example specifically because it has 6 things, 6 participants in it. And to show you that this is why I have to caution that if a formula has a constant, it is unrelated to this, okay? If I just use this formula and didn't point that out excessively, someone might make a mistake when they go on to another formula, all right? So the 6 on top is a constant. Okay, now we're going to solve for this. So the order of mathematics, you would do 6 times 10, solve the bottom, 6 squared, 36 minus 1, multiply that by 6, then divide the top by the bottom. So you solve for the fraction, then subtract this quantity from 1, and that will give you your Spearman row. That will be the end result of the analysis. So go ahead and solve, and once you've done, so pause, solve it, then come back and check your answer. All right, let's see how we did. In this case, you should have, when you complete that subtraction from 1, which gets you below the value of 1.0, we are going to have an R sub row of 0.714. Again, if we turn this into a percentile, that's 74 or 71.42. If you look back to that original column in terms of, or that original slide where the strength was, you're going to see this is listed as a very strong correlation. Again, though it's not listed here, this is a positive one. So it's a very strong positive relationship between a team member's strength and their endurance. Okay, so this is the restatement of this. Technically, this is enough. If you had this written out, which you do need, this is officially the formal answer, and then just provide the interpretation, that would be a correct answer. This is just sort of a medium step. If you want to write this down, if it helps you, at least during the learning process, go ahead and do this. But I'm not necessarily looking for you to restate this. This is this. Those say the exact same thing, but this is the official formal final answer. And you need an interpretation for every analysis that we do. So even if it says it or not, you have to interpret it. In this case, the interpretation, it's a very strong positive one. So the higher a team's member in terms of their ranking of strength, the higher their ranking of endurance. Again, I didn't repeat myself because I had this listed. I have listed it as very strong. If you skip this step, you should say there's a very strong correlation between the two. Somehow do that. But again, technically, I should know that by saying the 0.71. Okay. Now, notice that that had a lot fewer steps in it. The steps went a lot easier. The problem is it doesn't work in every case, because if you have only interval data or only ratio data or interval ratio, you can do this. You can transform them into ordinal ranks and calculate it, but it's the wrong formula, which means the answer is wrong. You can still do it. It won't turn out something awful, but it was interval or ratio data. You were supposed to have done the Pearson. Because there was ordinal data, you're supposed to do the Spearman row. Okay? So if you choose the wrong formula, that's the thing that we're adding, then that's going to be a big mistake. I will try to give you any points that I can, but notice that if you calculate this, I was looking for the sum of the X column, if this was supposed to be a Pearson R. You don't have it. I would have been looking, if this was supposed to be a Pearson R, I would have been looking for the sum of the Y columns. I would have been looking for the X squares, the Y squares, the XY, and the sum of all those numbers aren't here when you do it this way. So choosing the wrong formula now has a huge consequence. So understanding if it's nominal, ordinal, interval, ratio now has a consequence if you didn't learn that. Knowing how standard deviations work. If you haven't learned that by now, or at least know what you're doing, go back and learn it, because now you're going to have to do that as part of other formulas, or at least some part of the standard deviation formula in the formulas. So again, these things actually, this isn't just professor bullshit, which I understand sometimes happen. When I said that those things we learned in the first part of the semester were important because we need them every step of the way going forward, I was not lying. If you don't understand nominal ordinal integral ratio, chances are you're going to choose the wrong formula. And that can happen multiple times going forward. So tag that down if you don't have it. But it should have gone well. Hopefully I didn't lose you along the way. Congratulations, you have just solved your first non-parametric test and your second correlation. Yay, woo, huzzah. Otto is napped out here. He's still drugged up from his injury. He would show excitement, but he doesn't give a shit. He is beyond caring at this moment. So know that internally my dog is rooting for you and thrilled with your accomplishments. If I show you a picture, he's curled up in a fetal position and really couldn't give a shit about your successes this morning. Okay, so there's our second one. Now we're going to gear up for number 3. And here's our next cartoon animal. And at least I named this one just for shits and giggles for myself. This is forewarning chicken. And that means that he's warning you that something is necessary. So you're going to need something from the past. And in this case, he's going to tell us that, he didn't say mean because I'm assuming you understand mean by now, but we're going to have to calculate standard deviations. If you don't have your formulas for standard deviation out and ready, again, there is a formula page with everything written down. It'll show up on screen as well, but when we get to lab, I'm going to expect you just have a formula sheet with you. You're going to need to know how to do the standard deviation to do this formula. So if you need to go back and refresh how to do that, go ahead and then come back and join us. So you're going to need the standard deviation knowledge along with the nominal ordinal integral ratio data to do this. Now, there should be a second warning from the forewarning chicken, but I didn't do it. It's just a note on the next slide. And it's going to start with that this formula is not in your textbook. And that happens. Again, sometimes the formulas in the textbook are different because there are multiple ways of getting down to the correct answer. I sort of said that I'm using formulas that have been student tested. People who have some fear of math feel most comfortable with these symbols and these formulas. This seems to be the most understandable way to do it. That's why I chose them. So I will differ from your book sometimes for those reasons. In this case, it's a topic the book doesn't have, but the book has stuff that we're not covering. So this is just what are we going to run across, or what might you run across in the kind of things that psychologists do that other behavioral science people or other sciences may not. So you won't run across this a ton, which is why some books include it, some books don't. But this is something if you're going into education, if you're going to do anything. So if you're going to graduate school and you're going to have to TA, let me be honest, in large universities, the one thing that changes is that sometimes grading is done by computers. We don't have that. We're a small place. If you're at a small college or a small university and a small graduate program, they may not have it by computer. They may have grading done by TAs. But sometimes it is done by computers. And if it is done, they spit out statistics. The professor wants you to, before you, so you're going to do all the scut work as the student. You're either going to grade them or you're going to have to run the computer center, have them graded, and then you're going to have to sort of give a summary to the professor. The joys of TAs and graduate assistants. I'm thrilled to have a Sammy, a great tutor, and someone students can go through. That's all that I'm going to have. I'm thrilled with that, but I would love someone to come grading my shit. But just hasn't happened yet. So if you are in that position, even if you're not using it for your research, as a graduate student who is working for a professor, hopefully you get an assistantship. If you're working on the teaching side of things, this is something that's going to come across. The most common way I use them or run across them is if I'm ever looking at exam questions and seeing, is this a good exam question or not? Over the years, I've tested questions out, and I know that on this particular question, I expect 80% of the students to get this one correct. I expect 100% of students to get this one correct. I expect 4% of the students to get this question correct. Now, truthfully, making an exam, all 3 of those questions should end up on an exam. You need some that you're expecting everybody or a multitude to get correct. you're expecting some where a segment of the population should be correct, and you should have some where you're going to separate out the A pluses from the A's and from the A minuses. Now, you don't want an exam that has a whole bunch of 4% get it right, and you don't want an exam where 100% of them get it right. You've taken exams from other disciplines, and you see that not everybody does multiple choice well. You may like it because every single question is a gimme. It's like, I don't even need to study and do well. You show up my class and it's like, holy hell, nobody got that right. Yeah, 4% of the class did. And that was there on purpose. I make sure that it's going to give me a relatively normal curve. But these things are also used for if you find yourself in the unfortunate position that you think a student is cheating in class, you can look to see what their answers are. And you have to sometimes go back and look answer to answer, what question did people get right? Which ones did they get wrong? And the understanding of which ones they got right is going to play a role in that. Canvas also does, by the way. I had to have one of the reasons your exam got delayed. You can fast forward if you choose not to listen to this. Sorry, I'm just on, a rant just started, so it's going to finish. One of the reasons your exam and homework is taking a little bit longer to get graded. There's some stuff going on that took me away from home. But the other reason is that I looked at Canvas and I saw some students taking an online quiz who sort of went questions up, then they apparently went to another file and then came back and answered a question, read the next question, seemed to leave the test and go to another file, come back. So I had some students cheating, and they were surprised. They got a little update that it's pretty obvious that I can find out if students are cheating. Anytime that window isn't the only window on your screen, Canvas is going to tell me. So I forgot to think about it. I didn't plan for it. It's the first time. There are other problems with doing a test online I was worried about. But they know that their exam, Professor Tim is looking to see, especially for those students who, on a 33-minute quiz, went off page 36 times. More than once a minute, people went to other pages. I'm going to be looking at their exams to see if that continues. And if so, we're going to go to judicial a little bit earlier than normal. Now, why did that rant happen? Well, it happens because rants happen. The other reason it happened is a number of our students, again, doing well in stats, and your stat and experimental grades, those are two that the grad schools are going to look at, and they're going to base assistantships off your overall record, but they will look at stats and experimental probably a little bit more closely. Along third would be whatever is important to that program. But stats and experimental in every program are going to be important. And the reason that it is something that is looked at is because they are going to be giving you tasks, whether it's, even though you're teaching, you're going to have to analyze data sets. You're going to have to look at data sets or printouts and look at things. So these skills are vitally important for doing well. We have been lucky that our training actually does help a lot of our students get assistantships, and they have sort of come back and said that when they're teaching and when they're doing research, yeah, they need to know how to do these things. And the good news is they are doing a little bit better than a lot of their peers when they're showing up, because we're kind of such assholes about making sure this stuff gets drilled in. So that's why this is important. That's why the sequence of statistics and experimental is vital for you guys going forward. And hopefully it will get you a leg up in getting something like an assistantship. But they're going to be choosing those things based on things like, can you make sense of the statistics of a grade printout and tell me what and how my students were doing and those sorts of things. Okay, sorry, that was another one of those long-winded ones. They're just going to happen, okay? Because even I can't talk statistics straightforward. You get the pause, I'm going straight through. Okay, so make sure you've got your standard deviation ready. Make sure you got all the other stuff ready. And let's look at the point biserial. Again, this one not in the textbook, so you'll have to come back to the video to do this. I don't think me printing this out is going to help you at all, so I think just go back to the video if you need to walk through this again. And you'll have the lab where we'll do another word through tomorrow before we get to the homework. So this is the point. So point biserial, the full name is a point biserial correlation coefficient. All of them are correlations we're doing, and all of them, the answer is the correlation coefficient. So that didn't really add anything, but point biserial is the term of this. And again, not in the text. Or I missed it. I looked at this early in the semester and didn't see it. So I didn't see it. So in some tests, it's there, some it's not. I just prepared for it not being there. This is also a non-parametric test. And again, non-parametric sort of being at least the presence of the nominal or ordinal data scales. At least one of those is going to be somewhere in this. Also a clue for the non-parametrics. When it gets to interval ratio, we're into the parametric statistics. Anything not interval ratio, we're in the non-parametric statistics. Okay, now this one actually has a use for nominal data. And this is the only correlation you can do where nominal data is part of this. But this has an extraordinarily limited kind of situation where only a certain kind of nominal data is acceptable. So this first point with all the underlining means that even if it's nominal data, most of the time you still can't do this. But in certain situations you can. This is going to be used when one variable is either interval or ratio, and the other variable is a dichotomous nominal variable. So dichotomous just means there's one of two values 1 and 2, on and off, male, female. We actually end up calling these things the male and female scores. It just means there are only two groups possible, and by being in one group, you can't be in the other. And nominal is just the name for it. So we call them the male, female sometimes just to sort of illustrate the idea of a nominal label. But in terms of the computers, we tend to code them as 1 and 2. So it will look like a number, but actually 1 and 2 don't mean anything numerically. It just means it's group 1 and group 2. Okay, so one column has to be interval or ratio data. So if there's any ordinal in this at all, can't use this formula. Okay, the one column that's the numeric value has to be interval or ratio. The other column has to be a nominal classification, and there can only be 2 groups. If there are 3 groups, can't use this. Okay, nominal variable, 2 groups only. So you can't have a third one and just say, I'll just ignore the third one and only look at 1 and 2, because we're going to be calculating the standard deviation for the entire group. So all scores matter in the standard deviation, so you only can have 2 groups in here. Now, here are different ways that they could be. Gender, male and female. Again, that's the one we're going to go with. I will use the term male and female a little bit later. It could be age grouping, a group of young people, a group of old people. Could be, again, in the example I think we're using, it's going to be what school we're coming from, SBC, Sweetbriar College, LC, Liberty, although it's Liberty University. I think this was originally Lynchburg College, but they are now UL or LU. They're LU, sorry, they're LU. I don't know, it's just the not us group. It's us. And by the way, whenever we're doing an in-class example and Sweetbriar is one of the groups, Sweetbriar group's doing better, and you're going to do significantly better. Just letting you know, I'm going to try to suck up to you guys just as much as I can to hope to win over some love, because I make you do math all semester. And at the end of the semester, you'll be like, oh God, term statistics, and then you get into experimental, and then I don't seem so bad. But when you're filling out the evaluation is when you're sort of at peak hatred. So, yay. I love those professors who at the end give out cookies, and it's like, we're not going to do anything, just bask in our joy of literature. And I'm like, here's a big exam, you need to know everything. Here, fill out your evaluation. Yeah. All right. Okay, so here's our formula. R, correlation, sub PB for point biserial. Again, you need those identifiers. If those identifiers aren't there, I'm going to assume it's a Pearson. And then you wrote the formula wrong if you include the formula for point biserial. What you say first is the analysis I'm expecting you to do. So if you get that wrong by not including these subscripts, you wrote the wrong formula down, and you'll get marked off for that. Okay. Also, if you write the formula down, you're going to get a point off. That's why I'm making you do this. And sometimes that's where your mistake is. So just look at this first one. We'll sort of come back and read the entire formula in just a second. But the first thing is the mean of group 1 minus the group of mean 2. Sometimes people will write that down, and they write it down as the mean of group 1 plus the mean of group 2. They just make the problem when they're taking it from the formula sheet and writing it down on their paper. They write the formula down wrong. That's also going to be knocked off. So make sure that you're writing the formula down. So I'm having you do it. Make sure that it's right. Okay. So RPB is equal to, first fraction is all in a one set of brackets. On the top is the mean of Y1 minus the mean of Y2. That's group 1 minus group 2, the mean score of them, divided by S. And lowercase s means the standard deviation. Now, why is it y bar rather than x bar? Because up to this point, x bar has meant mean. Typically, mean is done on one or more columns. So x bar means the mean of the x column. Y bar just means the mean of the y column. If we had a third factor, again, we can't do three of them in a correlation, but you can have multiple data columns. We could have z bar, which would be mean of the z column. That's just a filler. So the way that I set the point biserial questions up, the actual data is in the second column. So I'm calling it y bar rather than x bar, but it's still the mean. It's just the data we're taking the mean for is in the y column. Okay, so that first quantity is multiplied by the square root of the quantity p multiplied by q. So you would p times q, take the square root of that, and then take that set of parentheses, multiply it by the solution to the first set of parentheses, and that would give you the overall or the final result. At this point, look down here where y bar 1 and y bar 2 are the means of each of those two dichotomous groups. S is the standard deviation for the entire sample. I capitalize this. It wouldn't have hurt to put this in red, underline it. When you're solving the standard deviation, you're treating the entire data set as one group. You're not going to separate them into y1 and y2. Standard deviation is done on the entirety of the data set. So all data points in that column, not separated by group. P is proportion of the male scores, Q is proportion of the female scores. We'll get to that later. For this moment, it's a simple thing at the very end. We'll deal with it at the end. Okay, so step 1, write your formula down. That tells me that I'm going to need to calculate the means for the y columns in group 1 and group 2. I'm going to need to do the standard deviation. So I'm going to need that formula along the way somewhere. And I'm going to have to solve for P and Q, which if those were columns, which they're not, but if they were columns, I would then have to calculate the P and Q. Okay, in this case, it's just calculated differently. We're not using columns to do this. All right, but when I write the formula down for standard deviation, I also know I am going to have to calculate a column of squares, and I'm going to need to sum up some columns as well. All right, so that's why writing the formula down tells you what you're going to need to know. Okay, so let's just start with what would have been presented for you. So in this case, students from the different colleges took an exam. So this would be like our ACAT exam. During your senior year, you take this nationally normed exam. And we use that as an assessment of how well did our students learn, which is a marker of how well are we teaching our students. This is one of the factors that goes into why we change a curriculum, why we require certain things and not others. This is used for decision-making purposes every year, along with a lot of other things. So this is a common thing that if you were doing this, in this case, we want to see a correlation between the college you attended and the test score. So we know for each person how each individual student is doing. This particular student, who is a Sweetbriar student, scored in the 84th percentile of psych knowledge. The second person, also a Sweetbriar student, scored in the 90th percentile. You know, way to go. Even our lowest Sweetbriar student at 65, still better than most of the other colleges. We're comparing this against another college who is psych majors from another college who are using the same test. So this would mean if we knew that Lynchburg College was also using the ACAT, and we wanted to see the correlation between school and outcome on this test, but these are the only two schools that are using it, we would look to see the correlation between going to Lynchburg or going to Sweetbriar, correlation between college and how well you learn psychology. Okay, so it is still a correlation between two things, but the two things are sort of a nominal grouping. There's only two. You can't include another college in here and do this. All right, step 1, calculate the means for y1 and y2. So we know how to do that. You sum up the column. That's why I left this blank here. Sum up the means for the Sweetbriar students. I'm sorry, sum up the scores and take the mean. So 1, 2, 3, 4, 5, 6 scores. So sum these up, divide by 6. For the Lynchburg, sum these scores up and divide by 5, because there's only 5 scores, to give us the means for y1 and y2. And I know on the next slide, my face is going to be covering it. So let's move this over here. Okay, so we now know the mean for y1, the average score on this test of Sweetbriar students. Mean score is 79.17. The mean for the second group, which is the Lynchburg College students, is 50.60. Now, later, after we get to the t-test, we're actually talking about statistical significance. We're going to be saying, is this difference between these? We can see there's a difference. Is this a meaningful difference? Are these far enough apart mathematically for us to interpret them in a mathematically simplified way, which is making a statement about statistical significance, statistically significant or not. At this point, we're just saying here's a relationship. So our interpretation is more limited here. So we'll do more with these when we get to another set of tests. But for now, we can certainly see that just based on mean values, our students did better than the Lynchburg students. But as we learned with standard deviation, if we don't factor that in somehow, we don't know if this is a meaningful difference. And that's where correlations are weak. We can't sort of go beyond sort of a descriptional factor here. Okay, second step in terms of how we're doing this, because just the order in which someone would normally do this, we would start with, we have to figure out what that S is. We're not going to do part of the Spearman row, then go back and then do this. We would start with the things we can calculate up front. So we would be calculating the standard deviation second. That would probably be the second step we would have. So I'm going to put the formula up here, but oops, looks like I'm going to put the whole thing up here. So jot the formula down. Remember the two steps here, but what you're going to need to calculate are the y-squares. So each of these things squared, added them all up, get the sum of the y-squares for here, and the sum of the y's here. So again, calculate the sum of squares first, sum of the x squares minus sum of x squared over n, and then plug that into the standard deviation formula, the square root of sum of squares divided by n minus 1. So go ahead and solve for standard deviation. We've already done this. So the next step is solved for you. So I will have it all worked out to standard deviation. So pause until you get to that moment. After you solve for standard deviation, again, treating the entire group as one, compare your answers to what's on the next slide. And if it's correct, you can go forward. If not, go back and figure out where the mistake is. All right, let's look at the answer. So for summing this, and again, if you have this formula and you put the x's in here, I wouldn't have marked off. I know what you're doing. So we're getting the y column, so I just turn these into y's. First, I'll solve for the sum of squares. Sum of the y squares, square everything, sum them up. 54,574 minus the quantity sum of y, sum of y, 728, quantity squared over n. Remember, n in this case would also be pairs of scores. So we have 11 individuals who gave us scores on these two dimensions, so n is equal to 11. Solve for the sum of squares is going to give us a sum of squares of 6,393.63. Now, truthfully, I think I carried it out more, again, because you really shouldn't get it down to 2 decimal points until the very end. I just did this because I had to put it in the PowerPoint. It was slow going, so just knocked it off. But the squaring works. It doesn't change the answer too much. If you have a little bit of a squaring error, that's going to happen along the way. As long as it's carried out to 3 decimal points when you're actually doing the math, it's going to be just fine. Okay, so 6393.63, plug the sum of squares into the standard deviation. Standard deviation is equal to the square root of sum of squares, 6393, divided by n minus 1. N is 11 minus 1, so it's 10. So 6393.63 divide by 10, get that answer, then take the square root of it, and that will provide you with the standard deviation for this group. And the standard deviation is 25.29. Now, that is the only score that's going forward with us. The means are, but of this, we're not using the sum of squares anymore. This score is going forward. Here, again, because I had to put the cartoon animals in, I have Otto just randomly show up once in a while to yell at you. And there is his smile. I call it his Elvis smile, but that's like a few seconds before he starts growling. So that's his like almost angry. So he's yelling at you. Remember, he's a bit of an asshole. He's always going to be yelling at you. I'll play your game, little 9-year-old child from hell. I'm going to put my own dog in here. This is me yelling at you, but I'm trying to not yell at you. So my dog's yelling at you. That's how it works. I assume you wouldn't have figured that out if I didn't tell you, but it's always me yelling at you. Okay, once again, and it won't be the last time, even though every time I do this, I say it's the last time. I'm going to keep reminding you, you cannot do this just by letting me solve this for you. If you did not square each of those things and solve it before you got to this thing or got to this particular slide, you're doing it wrong. and it's going to cause mistakes. And I say this every year, and someone doesn't believe me, and every damn year it shows up. So again, for this class, if you're not doing the work and all the individual steps of it, if you're not watching the videos, if you're not working through everything, even though we did it maybe just the day before, you're going to do bad when it comes to the homework and the exams. I'm trying to help you. You may not like it, but I am trying to help you. This is the way it works, is by you doing all of this work. So do it. And if you didn't, shame on you. I guess that's all I've got. That's the only thing I can do right now. Okay, so we're going to take that information and just put it on the next slide. So you see up top here, we have all the information that we need going forward. So our mean of Y1, mean of Y2, standard deviation for the individual or for the entire group. Step 3, figure out the proportion scores. And that's the P and Q thing that we have in the formula itself. Now, here is our factual wolf, or I'm sorry, fox, that we had before to give us information. These are, P and Q are just proportion scores. And we're going to see these are really just filler terms. They don't really mean anything. P is one group and Q is the other group. That's all it means. It doesn't stand for anything. But because the people sort of creating these formulas name things so poorly when they give the symbols. Like the t-test makes sense because the lowercase t stands for t-test. The analysis of variance is the f-test. And the only f in analysis of variance is in the word of, which is the least important word in there. Yeah, they don't name things well. Psychology screws it up too, but mathematicians aren't any better. So sometimes it means something, sometimes it doesn't. In this case, P and Q only means group 1 and group 2, and they're the proportional scores of group 1 and group 2. Now, just as with the last one, there's one weird little thing here, and that is there's not a formula for this. I mean, I guess there is, but it's not one that's going to show up. So it is the number of people in, find a simple proportion. So we have 2 groups, Sweetbriar and Lynchburg. We want a proportional score of how much of our entire sample is made of Sweetbriar scores and what proportion of our sample is made up of the Lynchburg group. So how many scores belong to one college, one group, Sweetbriar, and how much belong to the other group, the other college, Lynchburg College. Okay, that's all that the P and Q stand for. So to get a simple proportion, the number who meet the qualification of being group 1, which is how many Sweetbriar students are there. There are a total of 6 Sweetbriar students out of a total of 11 scores. So for our first one, for P, 6 Sweetbriar students out of a total of 11 scores. 6 divided by 11 gives us our value of P. For Q is the proportion of the other group. We have 5 people who come from Lynchburg College, 5 total scores out of, 5 scores out of 11 total scores. So Q is 5 divided by 11. Okay, so 6 by 11 gives us our P score, 5 by 11 gives us our Q score. If we have an equal number, let's say there were 12 participants, 6 from Lynchburg, 6 from Sweetbriar, then both P and Q would be equal to 0.5. Half of them come from one group, half of them come from the other group. In this case, we have an odd number of scores. Proportion is number of people who fall into one group out of the total number of scores, and then how many fall into the second group out of the total number of scores. Okay, go ahead and solve for P and Q, pause, and then come back, and we will then plug all of this into our point by serial formula. All right, solving gives us a p-value of 0.55. So 6 out of 11 scores, 6 divided by 11. And for the Lynchburg scores, Q is equal to 0.45. 45% of our group comes from Lynchburg, 55% of our group comes from Sweetbriar. Okay, so here's our formula again. We're going to plug everything into the point by serial formula. And Y1, 79.17, Y2, 50.6, divided by S, 25.29, multiplied by the square root of P, 0.55, times Q, 0.45. So if you plug it in, this is what the next step should be. And then we are going to solve. And by we going to solve, I have already solved it. It's on the next slide. This is now you are going to solve it. So go ahead and solve. And obviously, again, pause. Solve for RPB. Try to do an interpretation of it. And then come back and we'll walk through the final answer you get. All right, let's look and see how we did on this. The total final answer that you should have. And again, here you can see I skipped the medium step just to show you that if I was looking for steps, this would be what I would require. Now, you would need to show the work for the standard deviation. Okay, that is part of the solution. So you would need to show that work as well because it is something you're solving for this equation. So that would also be up here. Just because it didn't all fit on the slide, I took it off. But if this was homework, if this was the exam, yes, you do have to show the standard deviations as well, or the work to get to the standard deviations. Well, I do need to know where it comes from. The mean, yeah, I'm not really going to require it, but standard deviation, yes. And the P and Q, you at least need to show me 6 divided by 11 and 5. You don't need to solve it. You can just have it 6 divided by 11 is equal to 0.55. I would have been fine with that. All right, but you do need to write the formula down as part of this as well in its raw form. And then this is part of the work, is making sure that everything is plugged in correctly. So when you solve for it again, I recommend as a person to include that step of what this is versus what this is. So sort of solve for what's in parentheses in case you do that last step of multiplication wrong. But the final answer after everything is plugged in correctly is also going to be just fine. Final answer, lowercase r for correlation, sub PB for point biserial is equal to 0.5620. So that would be a positive correlation, again, if it's not listed. And again, if it's a positive value on the calculator, it doesn't show the positive sign either. So the absence of anything means positive. If it's a negative value, it will have to embark on this to identify it. RPV is equal to, we turn into a fraction, decimals, 50, or from decimals, 56.20. 56 is in the strong category. So if you went back and sort of looked at the classification system, there's a strong positive relationship between the college you attended and the score on the national exam. So there is a relationship between college that you attend and the exam score, with Sweetbriar students performing better based on the mean performance score. Now, notice what I did there in this one is if I just said that there is a strong relationship, that really doesn't tell us anything. This is a nominal classification. Okay, it's not as one goes up, the other goes down. I mean, it sort of is in a real blocky way, but it doesn't really help me out in terms of interpretation. But as a nominal group, I know that there were 2 separate groups, so I must be concerned about those 2 groups. So an interpretation about those 2 groups probably should talk about them in some way. And what could I say from the information I have? And in terms of interpretation, we look to see what information we have. I know that there's a strong relationship between college you attend and your score. And I do have here, as part of what I was solving to get there, I have the mean scores. And I know that group 1, Sweetbriar, did better. Their mean score is higher than the mean score of Lynchburg College. So I can include that in my interpretation. Now, it stops there. I can't say that Sweetbriar students perform better than, okay, although I sort of do. But I include it by saying based on the mean performance score. I'm limiting it. I actually limit that by saying this is based only on the mean. This is not saying this is a statistically significant difference because I didn't do that test. Okay, we're gonna learn to do it only with the t-test and beyond. I'm not asking you to do it here. But I would stop here and just say it's linked to the means. And that tells me that my interpretation is limited. But it is a piece of data we have. It is important to understand it, so I would want to include that in my interpretation of the data. I hope that makes sense. You'll, again, get used to this and we'll do a little bit of trial and error as we go through more examples and on the homework. So we'll get some more practice on doing this as we go through. Okay, there you have done your 3rd correlation of the day, and you have now solved the point biserial correlation. So 3 of them today: Pearson R, using interval ratio data, Spearman row, or just R sub row, for when we have at least one of the columns ordinal, the other column at least ordinal, and then finally point biserial. One column is at least interval ratio, and the other column is a dichotomous nominal variable. Those are the ones that you are responsible for, and you need to be able to identify them as which type to sort of go into the correct formula. So again, that's part of what you're responsible for heading into exam 2. Rewatch this. work through them again if you had any problems. During the lab video, there'll be another walkthrough of all three. So we will have another chance to go through this step by step together. Make sure before you sit down for that one, you have the lab data sets ready. And if you have that, then you're ready for the lab. Obviously, you have to wait till I post it, but the lab on Tuesday is going to be working through each of these a second time. So we'll have another chance to do this if it didn't quite gel this time. All right, there you go. That is our Monday. Yay, data. And me awkwardly getting off and talking to myself as I do so.